Alright, so if you guys have been following the Nvidia hardware scene, specifically about their consumer graphics cards, you may have seen that they're about to introduce a new microarchitecture called the Ampere Micro-Architecture. Now, this was revealed a few months ago, however, cards using this microarchitecture are still pretty thin on the ground. We know that we've got the A100 accelerator, which honestly, you can game on, but I'm not going to spend $200,000 on it. But in terms of Ampere, let's go over some specific technical specifications that are not necessarily confirmed, but something that we can reasonably expect. So first off, we can reasonably expect CUDA compatibility 8.0. So basically all that means is that each generation of Nvidia GPU, they update the CUDA core microarchitecture to a new version. So for example, the Pascal and Volta CUDA cores, well, they're technically the same and they have the same underlying DNA. From a technical level and from a specification level, they're technically different. However, it's not because they can do things that are suddenly new. It's just because over time they improve processes, make things more efficient, and can overall generally improve their engineering. So overall, CUDA compatibility 8.0 seems great. TSMC 7 nanometer FinFET process, once again, also seems pretty realistic. However, my question is, I know TSMC is pretty full of AMD orders. So if you guys don't know how printing CPUs work, from my understanding at least, and I could be getting certain details wrong. But from my understanding, how it works is TSMC or Global Foundries or basically say, I don't know, Intel, someone who prints CPUs, right? If you have 1,000 wafers, that means that, for example, AMD can buy 500 of them, Intel can buy, I don't know, like 250 of them, and Nvidia can buy the last 250. And on each of those wafers, what they'll end up doing is putting each company's specific design on it. So for example, say that you're, I don't know, AMD, and you're trying to print some of your Zen 2 CPUs. What you'd end up doing is you'd end up finalizing your design, finalizing all the circuitry, and then you would end up sending it over to TSMC to print onto the actual wafers that you're buying. So TSMC 7 nanometer FinFET seems pretty realistic, and if it's true, then it's going to be pretty incredible because Nvidia on 12 nanometer still crushes AMD on 7. So yeah. Next thing we can expect is a new generation Tensor core, which honestly sounds pretty incredible, based on some leaks that I've not necessarily heard, but I've, I guess, observed from a couple different people, is that with the new Ampere cards, what they're going to be using the Tensor cores for isn't necessarily strictly for RT or DLSS. Obviously, you're still going to be able to use them for that. Obviously, it's going to make a ton of sense to use Tensor cores for DLSS. You don't want that running on the standard shaders. But what that ends up meaning is that they can use it actually to compress and decompress assets when streaming in and out of memory. So what that ends up meaning is that your memory bandwidth, while technically higher than GDDR5, GDDR5X, since they're using, I'm assuming, the latest GDDR6, which is still pretty freaking fast. So basically what that means is that you can multiply your memory bandwidth, not necessarily by anything that's like linear, but for example, say that you're trying to stream, I don't know, 20 gigabytes of assets on a 15 gigabyte per second bus. What that ends up meaning is that you can, for example, compress it down to, I don't know, maybe 14 gigabytes. And then once it's through the bus, you can then use the Tensor cores to take it from a little package and then decompress it into all the information that you need. So obviously that's a huge improvement. Specifically for the new Ampere cards with A100, I know they're using HBM2E, I want to say, and it's using 2.4 gigabit per second HBM2, which is honestly significantly faster than even what Pascal used, which was 1.4 gigabyte per second. And on top of that, they're also supposed to be using a wider bus. We're moving up from 4096 bit up to 5120 bits, or roughly 5 kilobytes. All right, so I just caught myself in my infinite wisdom. I didn't mean to say gigabytes per second. I meant to say kilobit per second, because obviously bits don't translate straight into bytes. However, memory bandwidth is supposed to be higher, specifically with the new HBM2E. I read somewhere that you can get anywhere between 1500 gigabytes per second to around 2 terabytes, which is freaking crazy. Because I remember when 2 gigs was considered a lot, and that's all the RAM you'll need for years. But no, we're moving into 40 gigabytes of VRAM on the high-end Quadros, and I'm guessing server GPUs at 1,555 gigabytes per second. Holy crap. Oh, that's a lot. But in terms of general specifications that we don't have any rock solid specifications for, let's say, the RTX 3090. Obviously, there have been some leaks talking about that card. However, in my personal opinion, I'm not going to trust any of the specification leaks. Obviously, some of the microarchitecture leaks, such as, we're going to be using 3rd gen color compression or 4th gen color compression, or, I don't know, PCIe 4.0. That kind of stuff to me seems realistic, and it's something that I trust with my head, and it makes sense, I guess. I wouldn't necessarily trust these hardware leaks, because what that ends up meaning is, let's say you find online that, the RTX 3090, for whatever reason, has 6,912 CUDA cores, let's just say. Now, the thing is with CUDA cores, they're specifically meant to use for floating point 32-bit numbers. What that ends up meaning is that you have like ints, floats, doubles. Basically, all a float is it's just a double with the shorter memory allocation. And all the float is it's just basically a decimal point. So, for example, let's say you have like 1, 2, 3, those are all integers, but 2.25555 bar, whatever, for example, 3.33, 1/3, 2/3, 5/4, that kind of stuff are all floats and doubles. So basically what that means is that you actually need more memory than an int, but that also means that in order to convey the same amount of information using a float, it takes literally more memory. So that's why generally using ints is considered not necessarily a stronger form of computation. However, what it can lead to is, if you remember back in the PlayStation 1 days, the geometry kind of like kept morphing. So like the geometry would stay here, you'd turn, and then all of a sudden it would change a little bit, even though it was supposed to be stationary. That was because the PlayStation 1 or the PSX, whatever you want to call it, didn't actually have a floating point unit. It only calculated things using integers, which means that if you have a grid, so for example, let's say you have a game engine, how it ends up thinking is it thinks things in terms of a grid. So you have X and Y, and then you also have Z going up. What that ends up meaning is that if you are using floats, you can say, let's say you can go over 2.2, up 3.334, and to the right, let's say 2.9. If you have ints, all you can do is go over 2, up 3, and over 1. So it ends up constricting what you can actually do. It ends up causing these weird geometry morphing issues. So generally you need to use floating point numbers for this kind of stuff, which is why that you can't necessarily use 4-bit and 8-bit integers or floats even for machine learning workloads. I know that in the consoles they were talking about, we can divide our 32-bit floating point buses into 16, 8, and 4. So if you remember back to rapid packed math, that's basically what it is. However, if you have any computing experience, integers by default are usually anywhere between 16 to 32 bits, which means that you can basically adjust 16 or 32 bits, which is just a 1 and a 0, to represent a certain number. So what that ends up meaning is that you can literally put bigger numbers in memory if you're using a 32-bit float or a 32-bit int rather than a 16-bit float or a 16-bit int. So obviously these microarchitectural details are, to me at least, pretty impressive. However, if you're looking specifically at them, like we're tying back into the 6,912 CUDA core issue with the A100, obviously specifications for that card are pretty much confirmed by Nvidia, but they're consumer level cards, which are supposed to be coming either later this year or early next year. And I'm going to go ahead and say probably either super late this year or super early next year due to the pandemic. But in terms of actual specifications, obviously, even if they are true at the time of leaking, they can change them. They can obviously make some sort of last-minute efficiency change, meaning they'll need less CUDA cores, or meaning that they can increase clock speeds so it can run faster. So yeah, obviously I wouldn't trust these specifications, but honestly, that's just my 2 cents. Obviously, most of these architectural details I think are pretty safe to assume that they're pretty legit. CUDA compatibility 8.0, like I said, seems pretty legit. TSMC 7nm seems pretty legit. 3rd gen Tensor cores, obviously, is going to be a huge game changer with compressing and decompressing assets. NVLink 3.0, which is moving up to 50 gigabit per second, which is pretty good. Obviously, it's not necessarily enough to run an entire PCIe bandwidth, an entire PCIe bus off of, but it will definitely help because NVLink, in my understanding, is meant to, instead of having 2 cards where they're working together, they're literally 1 GPU in the terms of the actual computer. So that's just my understanding. I could be way oversimplifying it, but it's an evolution of SLI, and it, I'm hoping, is a huge game changer. However, other things such as PCIe 4.0 seems pretty legit. Only thing I'd be concerned about, though, is PCIe 4.0 uses a ton more energy than PCIe even straight 3.0, which is what I use in my system. So obviously power consumption is probably going to be a little higher, but at the same time, the shaders are going to use significantly less power because they're on 7nm. And if you watched my last video, you'll know that smaller transistors literally means that you can lower the voltage, so you can use less energy. But like I said, not necessarily expecting these things to be necessarily cheap. The GPU die size that I'm able to find for the A100 accelerator is 826 millimeters squared. And if you remember back to the 1080 Ti, that thing was rocking 610 millimeters squared. Yeah, but if you want to get even more technical, the 1080 Ti was rocking 15.3 billion transistors, and the A100 is rocking a 54.2 billion transistors. So yeah, that's quite an increase. Power consumption obviously goes up a little bit from 300 to 400 watts, whatever. But that's just my 2 cents, honestly. In my opinion, I think that all this Ampere stuff obviously is pretty exciting. I think a lot of it is true, and I don't think any of it is put out there to necessarily mislead people. However, like I said, this kind of stuff can obviously change. So if you're, for example, AMD or Nvidia, like I said, your specs are leaked, suddenly you make an efficiency improvement, and now your specs can change. Whoops, it's not honestly a huge deal, but it means that the leaked specs were wrong. So I'm honestly not going to save my hope until these actual specs are confirmed by Nvidia or AMD. Specifically Nvidia in this case, however, AMD with their Zen 3, RDNA 2, Big Navi, that kind of stuff. But in general, honestly, I'm going to go ahead and say that obviously be excited for these cards. I personally would not buy an RTX 20 series GPU. With the 30 series so close to coming out, obviously with the more intense RTX capabilities of the new cards, with the more efficiency of the new cards, honestly, I'm expecting some pretty great overclocking with these new cards as well. Just in general, I would wait and see what happens. Obviously, don't get specifically hyped and don't get excited over all these leaks and, oh my god, Moore's Law is dead said this and that, and oh my god, it's going to be awesome. Obviously, I'm not saying to not be hyped for certain things. However, at the same time, you also want to be reasonable, and I would take things with a huge grain of salt, at least until Nvidia confirms all of this information that we are getting. So thank you for watching, and if you enjoyed, don't forget to leave a like and subscribe, and click the bell icon so you'll be notified about all the future uploads. And it was fun talking, and I know this is kind of a weird style of video, I've never really done this before, and thanks for spending your time with me.